Hi, and a very good evening. Before we dive into the technical details, our team would like to extend a sincere thank you to our lecturer, Dr. Muhammad Ahmad Alomari, for his guidance and insights throughout this course on operating systems. My name is Justin, and I'm joined by my colleagues Rashwin and Udaya. Today, we are excited to present our analysis on process management and scheduling, a core pillar of modern computing that dictates how efficient a system handles multiple tasks. So, in the world of operating systems, a process is essentially a program in execution. To understand how an OS manages these processes, we must first understand the journey how a process takes from a moment is created to the moment it finishes a task. Our team has focused on analyzing five primary states within the process life cycle, which is new, ready, running, waiting, and terminated. This cycle is critical because it ensures the system resources like the CPU and the memory which are never wasted and that every process gets its fair turn to execute. So, let's walk through the five key transitions as shown in our diagram. So, first, it begins in a new state. Once the OS creates the process and admits it to the main memory queue, it moves to a ready state. From the ready queue, the CPU scheduler selects the process and dispatches it to the running state, where the actual execution occurs. Then, if a process runs out its assigned time slice or if higher priority tasks arrive, it is interrupted and moved back to ready. If the process needs to perform an IO operation like reading a file, it enters a waiting state. It only returns to the ready state once the specific event or signal occurs. Finally, once the task is finished and is aborted, the process enters the terminated state and is cleared from the system. So that's all for the process life cycle. Let me pass to the next person. Thank you.
Hello, my name is Tarachana Lakiravi and I will now explain about the process scheduling algorithm. As we can see, there is the table which gives us 8 different processes and then there is different arrival time and different burst time. So now with this data, I will use the process scheduling algorithm that is given to us, which is first come first serve, shortest job first, and round robin scheduling. So let's go for first come first serve. These processes are executed in the exact order they arrive. For example, P1 to P8. We can see that P1 arrives at time 0 and P8 arrives at time 7. So it will prioritize P1 first. And then we will go to shortest job first. This algorithm prioritizes process with smallest burst time currently in the queue. For example, when it's running P1, because its arrival time is 0, it should run P1 first. Once the P1 is done, it will choose the smallest burst time, which is P6, and then it will continue on to the other burst time, which is smaller than the rest. And then finally, round robin scheduling. Each process gets a small unit of CPU time, which is called quantum, before being preempted. So for example, later on there will be two examples on quantum 2 and quantum 4, but as a small brief, I can tell you that let's say in P1 the burst time is 6, but then the time quantum wants to can only take 2, so it will take 2 of the burst time and then it will go on to P2 and then it will go on to P3 and so on until P8, and then it will come back to process 1, and then it will take another 2 out of it, and then it will continue to process it and so on, and until it is done it will always comes back to the process. So that is about process scheduling algorithm. So now let's start with the first algorithm, which is first come first serve. So I've provided a Gantt chart, the tabulated data for process the arrival time, burst time, completion time, turnaround time, and waiting time in milliseconds. So now let's look back at the Gantt chart, and we can see that we have followed the algorithm by going from process 1, process 2, process 3, and so on to process 8 step by step. And then with all this tabulated data, we have found the average waiting time for this algorithm is around 16.5 milliseconds, and the average turnaround time is about 21.63 milliseconds. So this is a very simple implementation, but it suffers from high waiting time if long processes arrive first. So for example, let's say process 1 burst time is around more than 10 or 12, and then process 2 is just 2 millisecond burst time. So it takes a very long time for process 2 to start, and then it goes so on and so on. So this is what first come first serve is all about. So then the next algorithm, which is shortest job first. So as I've given above, there is a Gantt chart and a tabulated result, and finally the observation that I've provided. So let's go back to Gantt chart and the tabulated result. The tabulated results are similar to the one up in first come first serve, uh, where there is process, arrival time, burst time, completion time, turnaround time, and finally waiting time. So, in shortest job first, we should always remember that even though the first process is bigger than the second process, we should always look at the arrival time of these processes. If all the processes arrive at the same time, and then shortest job first can choose the smallest burst time and execute it first. But in this scenario, the arrival time of each process is different, and process 1's arrival time is in 0 millisecond. So, as big as its burst time is, we should prioritize that first. As we can see in the Gantt chart that I've provided, I have started with process 1. And then we will go to the smallest process after process 1, which is process 6, which has the burst time of 2. And then we finish process 6, we go to the next smallest one, which is process 4, and so on, which is process 7, 5, 8, 3, and 2. So in this shortest job first algorithm, I have observed that the average waiting time for the entire algorithm for the process to be completed is around 11.38 milliseconds. And then the average turnaround time is around 16.5 milliseconds. And we can mathematically optimal for minimalizing average wait time in this scenario. So as we can see, the shortest job first is the fastest compared to the first come first serve. So it is optimal compared to the first come first serve. All right. So now we are at the third algorithm, which is round robin scheduling with quantum 4. So I have provided the Gantt chart, the tabulated result, and my observation. So before I start with my Gantt chart, I should explain about the quantum 4 and how it works. So let's take an example of process 1. In this, the process 1 has a burst time of 6 milliseconds. So in this quantum 4, we'll only use 4, and then it will skip to the next process, which is process 2, which has 8 milliseconds of burst time. It will only use 4, and then it will continue on to process 3 and process 4. Now in process 4, the burst time is smaller than quantum 4. So the process 4 will be done in one run. It the burst time can be smaller than 4, but if it's higher than 4, it will be halted, and then the next process will continue, and then it will go on until it comes back to the process where it halted. So now, as I explained it earlier, we will see the example in the Gantt chart. So as we can see, the process 1, only 4 of its burst time has been used. And then it jumps to process 2. And then only 4 of its burst time has been used, and it jumps to process 3, and that continues. But in process 4, since it only has 3 millisecond of burst time, the process is already completed. And then it goes to process 5, 6, and since 6 is smaller than quantum 4, it will be done. And then it goes to 7, because 7 has 4 millisecond of burst time and the quantum is 4, process 7 is done on the first run too, and then it goes to process 8. And then we can see that process 1 comes back again at the 29th millisecond of the time, and then it will finish up the process 1, and then process 2, process 3, process 5, and process 8. So it is all done. So the observation is the average waiting time for this entire process to happen is around 22 milliseconds, and the average turnaround time is around 27.13 milliseconds. So round robin improves the fairness for each processes, but also increases the waiting time due to frequent context switching. So this is about quantum 4 round robin scheduling. So now we are at round robin scheduling with quantum 2. As quantum 4, quantum 2 is not that much different. But since we can see in the Gantt chart, there is more frequent changes of context switching, which you can see where there is process 1 happened 3 times, process 2 happened 4 times, and then process 3 happened 3 times, and so on and so on. So it is almost similar to quantum 4, but the context switching happens more frequently here because the quantum is set to 2. So you can see in the tabulated result where, and also the observation where the average waiting time is around 22.38 milliseconds, which is longer compared to quantum 4, and then the average turnaround time is 27.50 milliseconds, which is also longer compared to quantum 4. So by decreasing the quantum size, it increases the overhead and average time due to more frequent quantum switching. So as I said earlier, in the lower the quantum time, the frequent the context switching will happen in each process.
Hello, my name is Rashwin and my matrix number is B122310346. We're talking about the performance comparison summary. So, based on this table, we can see there is the three algorithms: first come, first serve, shortest job first, round robin with a time quantum of 4, and round robin with a time quantum of 2. So based on this four, we can see that the shortest time shortest waiting time, shortest turnaround time, shortest average waiting time, and average turnaround time goes to shortest job first. So we can say the best performer is shortest job first, followed by round robin and first come first serve. So based on the questions and the task given, the best algorithm to choose is shortest job first. Okay, so why shortest job first is the best choice? Firstly, is the efficiency. It provides the shortest average waiting time by clearing shorter tasks, like in the previous question, P6 and P4 first. The next is throughput. The system clears the queue faster, leading to higher efficiency. So if there's a long queue, the shortest job gets cleared first, which makes it very efficient. The next is lower overhead. Being non-preemptive, it avoids context switching costs associated with round robin. Okay, so next is strengths and weaknesses. For first come first serve, it's simple, fair, and there is no starvation. But the weakness is it leads to high waiting times. For shortest job first, the strength is that it's very efficient for short tasks, but the weaknesses is long processes, like in the previous question, P2 can face starvation or may never run. The last one is round robin. It is excellent for time sharing and responsiveness. It's one of the strengths. The weaknesses, it suffers from high overhead. Okay, so for the conclusion, the choice of algorithm significantly impacts the system's responsiveness and efficiency. So, in the specific task given, Shortest job first minimize the idle time and waiting duration the most effectively compared to round robin and first come first serve. So it is important that you ensure you choose the correct algorithm for the task given. So I'd like to say thank you to everyone, and thank you especially to our lecturer in Alomari for guiding us throughout the subject, which is operating system, and making it really easy for us to understand. Thank you so much again.